we're continuing with this idea of optimization. I'm doing a lot of these videos because, quite frankly, I was not very good at it when I first went through here, and I've learned a lot since then. And so I thought I'd pass on a little bit. The very first thing is, of course, we're going through these 5 things that we've been talking about this whole time. And so we have a list, kind of a setup that we need to go through each and every time. This one's a little different and doesn't provide us with as much information necessarily. We kind of have to derive everything ourselves. And so a rectangular package to be sent by Postal Service can have a maximum combined length and girth, the girth being the perimeter of the cross section, of 108 inches. Find the dimensions of the package of maximum volume, and because, if you're going to pay for it, heck, you want to shove as much stuff in there as you can. All right, so now we're going to assume the cross section is square. And so let's go ahead and just draw this out. I've got a square bottom. Ooh, man. I've got some kind of a height or a length. And so here's my box. And now you might want to include some kind of a hidden lines here just to make it a little bit easier on the eyes. And so we can go ahead and identify this. We said that we're gonna have a square box, and so this will be our X here and X here. And now we have no idea what our length is going to be. So let's just call it L. And so as we look at it, the X squared is just the area of our box, or the area of the base of the box, and then our length is just the height of the box if we stand it up on end. All right, so we're going to need, because of this here, let's go to step 1, make a list of all variables and all known variables. Okay, now I always like to draw a picture, and I didn't put that in there, but man, if you can draw a picture, that's going to lead you in the right direction typically. So make a list of all variables. Let X, this is going to be the width of the square base. And you need to go through this. This is very important. Most students will skip this part thinking, oh, this is beneath me. I don't need to do this. And then they forget what they're doing. And so write this down. X is the width of the square bottom. Now, you don't really need to put X is also the height of the square bottom because, well, it's a square. But you need to at least write something down. And so L, this is the length. Ugh, that's awful. Forget it, I'm not doing it. It's been so long since I've written anything. I usually only write limit in cursive. This is the length of the box. Okay, so let's go ahead and make some assumptions here. The second thing that we want to do is we want to determine the equation or equations to be optimized. Okay, and we want to put them in the variables that we have. We don't want to put any new variables in there. Otherwise, we need to declare them and define what they are. And so we want the maximum volume. Well, the volume for a rectangular solid is the length times the width times the height. Well, putting that in in the definitions of our variables, we have the length of the box, and we have the width of the square bottom is X, and the width of the square bottom is X, which is LX squared. Okay, well that's just fine. So now we need, typically, very typically, you're going to need at least one supporting equation. The reason being is your equation that you want to maximize or minimize, the equation you want to optimize, is going to have more than one variable in it. And so we need to, since we don't deal yet in multivariate calculus, we want to go ahead and shrink it all down to one variable. All right, so we have another piece of information here. The combined length and girth, which is the perimeter of the cross section, is 108 inches. And so if we take a look at that, then we say that 108 inches is equal to the length plus the perimeter of the cross section. The perimeter is 4x because we have 4 x's. And so what we can do is we can solve for L simply by subtracting 4x from both sides. So we get 108 minus 4x is equal to L. And now we can substitute that into our volume equation so that we have our volume is equal to L, which is 108 minus 4x times x squared. And you can take the derivative and at this point, if you wish, and use the product rule, I am going to simply just distribute. It's going to make it a little easier. 108 x squared minus 4x cubed. And now the derivative with respect to x is equal to 216x minus 12x squared. We need to set that equal to 0. All of our maximums or minimums happen at critical points, which is where either the derivative is undefined or does not exist, or the derivative is 0. In this case, it exists. And so we have 0 is equal to 216x minus 12x squared. And so the question being, of course, is 216 divisible by 12? And if we just do some quick calculations here, we get 56, we get 56 is 72, 6, so that's 18. 18 and 12 is 216. And so we're looking at 0 is equal to, we can factor out a 12. And when we do that, a 12x, I apologize, a 12x, and when we do that, we get 18 minus x. Okay, so we took out a 12x, we get 18 minus x, and so x is equal to 0. Or, and that comes from the 12x, or x is equal to 18. And so, well, since x equals 0 is not feasible, and I've seen some books say, okay, well, limit the domain. Well, yeah, I don't do that explicitly. At this point, you should have developed a problem-solving set and know some physical limitations of the world. And so I just look at it as, oh, x equals 0. Well, that means the box doesn't exist according to our definition of x, and so we don't have to worry about it. Well, yeah, obviously you're going to have kind of a, but anyway, x equals 18 is much more feasible. So you can go ahead and take the second derivative if you so choose, just to make sure that that is in fact a maximum. When you do that, then you get 216, and this is minus 24x, and 24 times 18 is going to be a negative, and so that you have concave down, which implies a maximum. Second derivative test. So that's our value of x. If we have x is equal to 18, then 108 minus 4 times 18 is equal to L, which is that's 36, 72. 72 goes up, that's 28, that's 36. And so we have L is equal to 36 inches. So there we go. We want 18 inches square, and we want it 36 inches long. Now, a more important thing would be, assuming that we have this restriction no matter what the size of the box, exactly what is the ratio between x and L that must exist to get a maximum volume? Huh. So that would be a good engineering question. Maybe we'll do that next time.